Good day and welcome to our class. Today we shall be discussing on consequences of Cauchy integral formula. But before that, let's consider some definitions. Number one, let's consider what we call pole of order n. And these define as. So we have these definitions. The first one is pole of order n. A function that is analytic in the disk has a pole. We say that it has a pole of order n if it can be written in this format. F of z can be written in this format. Then we say that this z naught is a pole of order n, where this phi of z is analytic as z naught, and z naught, phi of z naught is assumed not to be equal to 0. So that is how we define it. If this n, if n is 1, we say that is a simple pole. If n is 2, we say that is a double pole, or we just say that is a pole of order 2. But if n is 1, we say that is a simple pole. Another one is Megamorphic function. We say that a function is meromorphic if it is analytic everywhere in a domain, except possibly for poles in D. That is, if a function is analytic everywhere except at some singular point, then we say that the function is meromorphic. Unlike entire function, which is analytic everywhere. So example of meromorphic function, I can say that there's a 2z plus 1 over z minus 1. Here, z is equal to 1. Here, if you make this to be equal to 0, z is equal to 1. Here, z is equal to 1. It's a singular point. So this function will be analytic at every point except at this z is equal to 1. In that case, this function is a meromorphic function. Now, we all know Cauchy integral formula before. So the first one, we all know that Cauchy integral formula states the following. I believe we can still recall this, the Cauchy integral formula. So it states this: if you have n is equal to 0 here, but generally the Cauchy integral formula states this. So you should remember the Cauchy integral formula. Let's now move to the consequences of the Cauchy integral formula. That will lead us to theorem. If they say that consequences of Cauchy integral formula, that is, what are the things that Cauchy integral formula has caused, or what are its usefulness, or what are its effect. So it will lead us to the following theorem. These are Theorem One. The first theorem, we call it Cauchy's inequality. If f of z is bounded and analytic inside and a simple curve C, a closed curve C of this disk, and if absolute value of f of z is less than m, that is, if f of z is bounded for every z in C, then this happens. So we call it Cauchy's inequality. That is Cauchy's inequality. Merely looking at it, you see that it's from the Cauchy integral formula. So in that case, we need to recall from the Cauchy integral formula that f of z naught is equal to, if you recall from Cauchy integral formula, this is the Cauchy integral formula. If you recall that, so you will now see that f of z naught is m factorial over 2 pi I into integral c f of z over z minus z naught raised to power m plus 1 dz. Now, you see that there's an absolute value here, so we take absolute value of both sides. So that is, we put absolute value there, we put it there, we put it there. Now, by theorem of absolute value in integration, this will be less than or equal to, when we put, there's an absolute value 2 here, so it will make this, the absolute value will make this I leave, it will remain ordinary pi. Now, when we bring this absolute value inside the integral, we are going to have less than or equal to. it will no more be ordinary equal to, it will be less than, so it will be absolute value of f of z over z minus z naught raised to power m plus 1 dz. Now, this will be equal to m factorial over 2 pi into, this is absolute value, by theorem of absolute value, we have this, over z minus z naught raised to power m plus 1 dz. Now, we remember that here we have been told that here the absolute value of z naught is less than or equal to m. So this will be less than or equal to m factorial over 2 pi. This will be ordinary m over z minus z naught raised to power m plus 1 dz. Don't forget, the way we prove the Cauchy integral formula, we can say that let z minus z naught be equal to r exponential I theta, so that our z is equal to z naught plus r exponential I theta will differentiate. The z is equal to, this will be ir exponential I theta d theta. So when we have that, our theta is in between 0 and 2 pi, which is 360 degrees. Therefore, our absolute value of f of z naught will be less than or equal to m factorial, this m factorial over 2 pi into integral m over, don't forget that there's an absolute value here, m over, we have said that z minus z naught is equal to, z minus z naught is this, so let's put it there. So this is absolute value of r exponential I theta, absolute value raised to power m plus 1. Also d dz, these are dz here, that is absolute value of ir exponential I theta d theta. Now, from this place, the absolute value, we make I to be 1. Also, we know that absolute value of exponential I theta is 1 as well. Absolute value of I is also 1. So in that case, all the I will leave, this I theta 2 will leave. What we are going to have left is 2 pi I, m factorial over 2 pi, 0 to 2 pi. We are writing theta now, m divided by, what we are going to have left is just r over n, because this r we cancel this 1. Then we have d theta. From this place, we have m factorial over 2 pi r raised to power n. When we integrate this, we should have theta, because it will remain only the theta inside. Then we have 0 to 2 pi. Finally, without wasting my time there, we are wasting my note. This is m factorial over 2 pi r raised to power n. The whole of this thing should give, after substituting, should give me 2 pi. From this place, 2 pi cancel 2 pi. What we have left, okay, sorry, there is m there, this m. I forgot to put the m. There's m there. So what we are going to have left is m factorial m over r raised to power n. So that is what we have to prove, and we have proved it, mn factorial. So this is the proof of the Cauchy's inequality. Let's consider another theorem. So our theorem 2, we call it Liovilles theorem. The theorem says that if a function is bounded and is entire in a complex plane, then the function is constant. That is, if a function is bounded, that is, if absolute value of that function is less than certain m, and is entire in a complex plane. Entire simply, we have know what entire means. If a function is analytic everywhere in a complex plane. So the Liovilles theorem says that that type of function is what? Is constant function. So let's prove it. Let's prove the theorem. So we use the theorem one, which is the Cauchy's inequality. We use Cauchy's inequality, the one we just proved. You know, we have just shown that f of z naught is less than m dot m factorial over r raised to power n. Now, so that means if n is 1, we can simply have it to be f prime z naught is less than or equal to m over just r. Now, let's take r tends to infinity. So as r tends to infinity now, what we are going to have is f prime of z naught is less than m over infinity tends to 0. So we can say it's less than 0. Absolute value cannot be less than 0. Then we'll say that it is equal to 0. So this simply means that f prime of z naught is equal to 0. And if we integrate both sides, f of z naught will be equal to integration of 0. That is simply constant. So that completes the proof. So we have completed the proof of Liovilles theorem. So because this function here shows that it's analytic everywhere by Cauchy's inequality, and also it is bounded. That is why we use Cauchy's inequality. Now let's consider another theorem. So our theorem 3, we call it Gauche mean value theorem. Now let f of x be analytic inside and C, then the mean of the values of f of z inside C is f of z naught. So that is, if you use the mean value in real analysis, so we express it like this. So if you look at it, it still resembles Cauchy integral formula. So let's prove it. So we recall from Cauchy integral formula, you know, it says that f of z naught is 1 over 2 pi I 0 to c is there, f of z over z minus z naught dz. So we recall this. As usual, we let z minus z naught be r exponential I theta. From this place, if you make z the set of formula, z will be equal to z naught plus r exponential I theta. When we differentiate this, we are going to have dz equal to ir exponential I theta d theta. As usual, 0 is less than theta is less than 2 pi. So we will continue from this place. Our f of z naught will now be 1 over 2 pi I into 0 to 2 pi now. Our f of z, this is f of z, this is our z now. This is z naught plus r exponential I theta over z minus z naught. So these are z minus z naught here, r exponential I theta. Our dz is ir exponential I theta d theta. From this place, exponential I theta cancels, r cancels, I2 cancels here. What we are going to have left is 1 over 2 pi 0 to 2 pi f of z naught plus r exponential I theta d theta. That simply completes the proof. Now let's take example on this Gauche mean value theorem. We are asked to evaluate this integral cos square pi over 4 plus 2 exponential I theta d theta. So merely seeing it, we see that it looks like that of Gauche mean value, which says f of z naught is equal to 1 over 2 pi 0 to 2 pi f of, this is f of z naught plus r exponential I theta. And if you make it the Euler formula, the whole of this will be equal to 2 pi f of z naught. So the only thing we need to know here is our z naught. So this is our z naught here. So here, our z naught is pi over 4. If you compare it, this is our z naught, this is our r, this is exponential I theta. So our z naught is pi over 4. Therefore, that integration that is given to us, cos pi over 4 plus 2 exponential I theta d theta, will be equal to 2 pi f of z naught. This is 2 pi. So this is our another thing we need to know, our f of z itself. Our f of z is simply, this is the f of z, cos is equal to cos square z. So forget about all this, is cos square z. So we said 2 pi f of z naught. So this will be cos square z naught. This is our z naught. Our z naught is pi over 4. So our answer is 2 pi cos pi over 4 is 1 over root 2. Then we have 1 over root 2 squared. Finally, if you simplify everything, our answer is equal to pi. In that case, the value of this integral is equal to pi. Let's take another example. Now I want to find the example 2. We want to find the mean of the values of f of z, where u is this over this circle. We need to first know what is our f of z. We have only known the u. So in this case, we need to apply Cauchy-Riemann equation. How do we do this? We find the u dx. The u dx is 2x. Y du dy is minus 2y. We know that this function is harmonic, because differentiating it once again, twice, it will become 0. So in this case, we can find our v by Cauchy-Riemann equation. We know that by Cauchy-Riemann equation, we all know that the u ds is equal to dv dy, and the u dy is equal to minus dv dx. Now let's use our dv dy here. Dv dy is equal to du ds. These are the u ds, which will give me 2x. From this place, if you find v, we differentiate 2x with respect to y. When we differentiate 2x because it's with respect to y, so our answer is 2xy plus f of x. Also, we need to find the second one. Here, we say that the v dx is equal to, if you transfer this minus, it will be minus du dy. And this is our du dy. The u dy already is a minus, so it will just become plus 2y. And we'll differentiate it as well. This is 2y. It is now with respect to x. We integrate with respect to x. So this is also 2sy plus g of y. And I told you, what's our v? V is the union of these two. So which is just 2xy is our v. So we will now see that our f of z is u plus iv. So what's our u? X squared minus y squared is given plus iv. This is our v, 2xy. We're supposed to put c there, but we don't need it. If you simplify further, you should be able to get z squared. I will not teach you this. You must learn how I arrive at z squared, because if I expand z squared, I must get what is here. This is how to do it. X plus iy all squared. When you are expand it, you should be able to get this. So our f of z is z squared. Now let me continue from another sheet. Now we continue from this place. Since we have now known that our f of z is z squared, also we are given this disk. We have z minus 2I is equal to 3. So we are having this z minus 2I is equal to 3. From this place, our z naught is simply 2I, while our r is 3. Our r is 3. By definition, we say 1 over 2 pi 0 to 2 pi. We say that the mean is 1 over 2 pi 0 to 2 pi f of z naught plus r exponential I theta d theta. Now, our answer is 1 over 2 pi 0 to 2 pi f of z naught. So this is our z naught, 2I. So, and our z is this. That means wherever we see z, we are going to put this there. So this is our f of z naught. So we are going to have, this is our z naught, 2I plus our r is known to be 3 plus 3 exponential I theta. There is square on it, all square d theta. Now, let's further. How do we now integrate this? We need to expand it. So let's quickly expand it and get an answer. When we expand, what do we have? We have, so I've expanded it now. Let us now integrate. When we integrate this one, we have 4 theta. When we integrate this one, we have 12I exponential I theta over I. And when we integrate this one, we have 9 exponential I2 theta over I2, or 2I over I2, 0 to 2 pi. Now, this will give me 1 over 2 pi. Let's put theta to be 2 pi. So this will be minus 8 pi. Put theta to be 2 pi. If you put theta to be 2 pi here too, we have 2 I cancel I. Don't let's stress ourselves. This is 2 pi I plus this is 9 over 2I exponential. If you put theta here, we have 4 pi I. Now, we subtract. As usual in integration, we subtract. When we subtract, when we put theta to be 0, this is gone. When we put theta to be 0, we have minus 12 exponential 0. When we put theta to be 0, we have minus 9 over 2I exponential 0. We know that exponential 0 is 1, so don't let us stress ourselves. For this is 1 over 2 pi into minus 8 pi exponential 2 pi I. If you use the formula, exponential I theta is equal to cos theta plus I sin theta. Cos 2 pi is 1, sin 2 pi is 0. So it will make the whole of this thing to be 1. So what we have there is ordinary 12. This one too, 4 pi, exponential 4 pi is also 1. So what we have here is just 9 over 2I. This is minus, this will give me 12. This is minus 9 over 2I. 9 over 2I is gone. 12 is gone. What we are going to have left is simply minus 4, because pi cancel pi. So in that case, minus 4 is the mean of values of this. Is the mean of values of this. And we have found it. So minus 4 is our answer.